let's say we want to solve a single variable equation. This is the problem that we started with. We want cosine of x to be equal to x. And let's assume when we're inputting cosines, we're inputting radians. That's the typical thing we do, is input radians. Well, in this case, if I want to solve this equation, I am simply going to create a function and then look for the roots. So let's go ahead and use Newton's method to approximate a solution for this equation. We're going to start with an initial guess of x0 equals the number 1. And we're going to approximate this time to within 3 decimal places. We'll see how we go about doing that in just a second. So we have an equation, and like we said, we're going to create a function in order to utilize solving this equation. Or we're going to create a function where the solution to this equation is a root of the function. If I want to create a function where this equation has a solution, which is the root of a function, all I really need to do is force one side of an equation to be 0. I can either subtract x or subtract cosine x. I think I'm going to subtract x from both sides. So we're going to get cosine of x minus x equals 0. If I look at that, then I can create a function, we'll call it h, which is cosine of x minus x. And the roots of h of x are the solutions to cosine x equals x. If that's my function, then the derivative of this function is going to be the derivative of cosine minus the derivative of x. So we take derivative of cosine is negative sine, derivative of minus x is minus 1, so you get minus sine x minus 1. My initial guess, the problem said let be 1. Let's plug in 1 into my function h. Again, make sure you're using radians as you are doing this, because if you're using degrees as you're doing this, you and I are going to get the different answers. So let's go ahead. Cosine of 1 minus 1 is negative 0.459698. That's rounding to 6 decimal places. If I plug in 1 into the derivative, negative sine of 1 minus 1 is negative 1.841471. Trying to make sure I rounded that to 6 decimal places. That's the hardest part, is not to screw up and write a number or an extra number where it shouldn't be. So we see we get negative 0.45. That means that 1 is not a root. So we can do a first iteration of Newton's method and keep going from there. This function is called h, so I'm going to change Newton's method to having a function labeled h. We're going to take 1 minus the fraction, negative 0.45968 divided by negative 1.841471. I ended up with approximately 0.750364. That's rounded to 6 decimal places, obviously. Now let's take some calculation, but we can do this. This is called H again. H, plug in 0.750364. You're going to get negative 0.0189233. Rounded to 6 decimal places, that's what we get. If I plug in that same value into the derivative, I end up with a negative 1.681905. So obviously, x1 is not a 0, but we are closer to the x-axis there. Let's do another iteration. This problem asks us to not do a certain number of iterations, but make sure we're rounded to 3 decimal places accurately. I'm going to show you how to do that in this case, but in any cases that we want. So to do our next iteration, we take x1 minus hx1 divided by h prime of x1, 0.750364 minus the output of the function divided by the output of the derivative of the function. I ended up with 0.739113. Notice how this is the same to 1 decimal place, but it doesn't round the same as to 2 decimal places that our original iteration did. So this means not 100% sure that this is going to be accurate within 3 decimal places. I basically want them to match up to within 3 decimal places of the next iteration, or the previous iteration, excuse me. So that means I got to keep going. I'm going to take h of 0.739113. I end up with a really small number, negative 4.664 times 10 to the negative 5th power. That's a very, very small number. As far as the derivative goes, when you plug in 0.739113, you end up with a negative 1.6736. As you can see, the third iteration is going to start at the second iteration. And it's going to change the second iteration by this factor here. The second iteration is the 0.739113 number. And it's going to change that by a fraction. The fraction is going to have a numerator of negative 0.0004664, and a denominator of negative 1.67. Now I can kind of see already that this means it's not going to change this number by very much at all. At least you can see in this, there's a lot of zeros here. And if you think about what this fraction is, this is going to be an extremely small fraction. So when you do this calculation, you're not going to expect that number to change by very much from the second to third iteration. Let's go ahead and do the calculation though. When I ended up doing that, I got 0.739085. You can see that this is very close to the second iteration. So if somebody asks you to round the root to 3 decimal places, you could say, well, I know that rounded to within 3 decimal places, that's 0.739. So the answer rounded to 3 decimals is 0.739. And that's the answer, remember, to this initial equation. Cosine x equals x. If you type in cosine of 0.739, you're going to get really, really close to 0.739. Once again, be careful that we're in radians when you're dealing with cosines and sines. So that's how this goes. You can see pretty clearly how once your iterations don't change by 3 decimal places, those first 3 decimal places are going to stick tight. Remember, you're always going to get better and better approximations as you do Newton's method. I would like you to try to use Newton's method to approximate the solution of this equation and start with an initial guess of x0 equals the number 1. Approximate to 2 decimal places. So approximate your answer to 2 decimal places on this one.